Designing Applications Around Dataflow, the approach of unbundling databases by composing specialized storage and processing systems with application code is also becoming known as the database inside-out approach, after the title of a conference talk I gave in 2014. However, calling it a new architecture is too grandiose. I see it more as a design pattern, a starting point for discussion, and we give it a name simply so that we can better talk about it. These ideas are not mine. They are simply an amalgamation of other people's ideas from which I think we should learn. In particular, there is a lot of overlap with dataflow languages such as Oz and Jutl, functional reactive programming FRP languages such as Elm, and logic programming languages such as Bloom. The term unbundling in this context was proposed by J. Krebs. Even spreadsheets have dataflow programming capabilities that are miles ahead of most mainstream programming languages. In a spreadsheet, you can put a formula in one cell, for example, the sum of cells in another column, and whenever any input to the formula changes, the result of the formula is automatically recalculated. This is exactly what we want at a data system level. When a record in a database changes, we want any index for that record to be automatically updated, and any cached views or aggregations that depend on the record to be automatically refreshed. You should not have to worry about the technical details of how this refresh happens, but be able to simply trust that it works correctly. Thus, I think that most data systems still have something to learn from the features that VisiCalc already had in 1979. The difference from spreadsheets is that today's data systems need to be fault-tolerant, scalable, and store data durably. They also need to be able to integrate disparate technologies written by different groups of people over time, and reuse existing libraries and services. It is unrealistic to expect all software to be developed using one particular language, framework, or tool. In this section I will expand on these ideas and explore some ways of building applications around the ideas of unbundled databases and dataflow. Application code is a derivation function. When one dataset is derived from another, it goes through some kind of transformation function. For example, a secondary index is a kind of derived dataset with a straightforward transformation function. For each row or document in the base table, it picks out the values in the columns or fields being indexed and sorts by those values, assuming a B-tree or SS table index, which are sorted by key, as discussed in Chapter 3. A full-text search index is created by applying various natural language processing functions such as language detection, word segmentation, stemming or lemmatization, spelling correction, and synonym identification, followed by building a data structure for efficient lookups such as an inverted index. In a machine learning system, we can consider the model as being derived from the training data by applying various feature extraction and statistical analysis functions. When the model is applied to new input data, the output of a model is derived from the input and the model, and hence, indirectly, from the training data. A cache often contains an aggregation of data in the form in which it is going to be displayed in a user interface UI. Populating the cache thus requires knowledge of what fields are referenced in the UI. Changes in the UI may require updating the definition of how the cache is populated and rebuilding the cache. The derivation function for a secondary index is so commonly required that it is built into many databases as a core feature, and you can invoke it by merely saying create index. For full-text indexing, basic linguistic features for common languages may be built into a database, but the more sophisticated features often require domain-specific tuning. In machine learning, feature engineering is notoriously application-specific and often has to incorporate detailed knowledge about the user interaction and deployment of an application. When a function that creates a derived dataset is not a standard cookie-cutter function like creating a secondary index, custom code is required to handle the application-specific aspects, and this custom code is where many databases struggle. Although relational databases commonly support triggers, stored procedures, and user-defined functions, which can be used to execute application code within the database, they have been somewhat of an afterthought in database design. See transmitting event streams on page 440. In theory, databases could be deployment environments for arbitrary application code, like an operating system. However, in practice they have turned out to be explaining a joke rarely improves it, but I don't want anyone to feel left out. Here, Church is a reference to the mathematician Alonzo Church, who created the lambda calculus, an early form of computation that is the basis for most functional programming languages. The lambda calculus has no mutable state, i.e. no variables that can be overwritten, so one could say that mutable state is separate from Church's work, poorly suited for this purpose. They do not fit well with the requirements of modern application development, such as dependency and package management, version control, rolling upgrades, evolvability, monitoring, metrics, calls to network services, and integration with external systems. On the other hand, deployment and cluster management, tools such as Mesos, Yarn, Docker, Kubernetes, and others are designed specifically for the purpose of running application code. By focusing on doing one thing well, they are able to do it much better than a database that provides execution of user-defined functions as one of its many features. I think it makes sense to have some parts of a system that specialize in durable data storage, and other parts that specialize in running application code. The two can interact while still remaining independent. Most web applications today are deployed as stateless services, in which any user request can be routed to any application server, and the server forgets everything about the request once it has sent the response. This style of deployment is convenient, as servers can be added or removed at will, but the state has to go somewhere, typically a database. The trend has been to keep stateless application logic separate from state management databases, not putting application logic in the database, and not putting persistent state in the application. As people in the functional programming community like to joke, we believe in the separation of church and state. In this typical web application model, the database acts as a kind of mutable shared variable that can be accessed synchronously over the network. The application can read and update the variable, and the database takes care of making it durable, providing some concurrency control and fault tolerance. However, in most programming languages, you cannot subscribe to changes in a mutable variable, you can only read it periodically. Unlike in a spreadsheet, readers of the variable don't get notified if the value of the variable changes. You can implement such notifications in your own code. This is known as the observer pattern, but most languages do not have this pattern as a built-in feature. Databases have inherited this passive approach to mutable data. If you want to find out whether the content of the database has changed, often your only option is to poll IE to repeat your query periodically. Subscribing to changes is only just beginning to emerge as a feature. See API support for change streams on page 456. Dataflow. Interplay between state changes and application code. Thinking about applications in terms of data flow implies renegotiating the relationship between application code and state management. Instead of treating a database as a passive variable that is manipulated by the application, we think much more about the interplay and collaboration between state changes, and code that processes them. Application code responds to state changes in one place by triggering state changes in another place. We saw this line of thinking in databases and streams on page 451, where we discussed treating the log of changes to a database as a stream of events that we can subscribe to. Message passing systems such as actors, see message passing dataflow on page 136, also have this concept of responding to events. Already in the 1980s, the tuple spaces model explored expressing distributed computations in terms of processes that observe state changes and react to them. As discussed, similar things happen inside a database when a trigger fires due to a data change, or when a secondary index is updated to reflect a change in the table being indexed. Unbundling the database means taking this idea and applying it to the creation of derived datasets outside of the primary database, caches, full-text search indexes, machine learning, or analytics systems. We can use stream processing and messaging systems for this purpose. The important thing to keep in mind is that maintaining derived data is not the same as asynchronous job execution, for which messaging systems are traditionally designed. See logs compared to traditional messaging on page 448. When maintaining derived data, the order of state changes is often important. If several views are derived from an event log, they need to process the events in the same order so that they remain consistent with each other. As discussed in acknowledgements and redelivery on page 445, many message brokers do not have this property when redelivering unacknowledged messages. Dual writes are also ruled out. See keeping systems in sync on page 452. Fault tolerance is key for derived data. Losing just a single message causes the derived dataset to go permanently out of sync with its data source. Both message delivery and derived state updates must be reliable. For example, many actor systems by default maintain actor state and messages in memory, so they are lost if the machine running the actor crashes. Stable message ordering and fault-tolerant message processing are quite stringent demands, but they are much less expensive and more operationally robust than distributed transactions. Modern stream processors can provide these ordering and reliability guarantees at scale, and they allow application code to be run as stream operators. Roman 2. In the microservices approach, you could avoid the synchronous network request by caching the exchange rate locally in the service that processes the purchase. However, in order to keep that cache fresh, you would need to periodically poll for updated exchange rates, or subscribe to a stream of changes, which is exactly what happens in the Dataflow approach. This application code can do the arbitrary processing that built-in derivation functions in databases generally don't provide. Like Unix tools chained by pipes, stream operators can be composed to build large systems around Dataflow. Each operator takes streams of state changes as input and produces other streams of state changes as output. The currently trendy style of application development involves breaking down functionality into a set of services that communicate via synchronous network requests such as REST API. See Dataflow through services. REST and RPC on page 131. The advantage of such a service-oriented architecture over a single monolithic application is primarily organizational scalability through loose coupling. Different teams can work on different services, which reduces coordination effort between teams as long as the services can be deployed and updated independently. Composing stream operators into Dataflow systems has a lot of similar characteristics to the microservices approach. However, the underlying communication mechanism is very different. One-directional, asynchronous message streams rather than synchronous request/response interactions. Besides the advantages listed in message passing Dataflow on page 136, such as better fault tolerance, Dataflow systems can also achieve better performance. For example, say a customer is purchasing an item that is priced in one currency but paid for in another currency. In order to perform the currency conversion, you need to know the current exchange rate. This operation could be implemented in two ways. In the microservices approach, the code that processes the purchase would probably query an exchange rate service or database in order to obtain the current rate for a particular currency. In the Dataflow approach, the code that processes purchases would subscribe to a stream of exchange rate updates ahead of time and record the current rate in a local database whenever it changes. When it comes to processing the purchase, it only needs to query the local database. The second approach has replaced a synchronous network request to another service with a query to a local database, which may be on the same machine. Even in the same process. Roman 2. Not only is the Dataflow approach faster, but it is also more robust to the failure of another service. The fastest and most reliable network request is no network request at all. Instead of RPC, we now have a stream join between purchase events and exchange rate update events. See stream table join stream enrichment on page 473. The join is time dependent. If the purchase events are reprocessed at a later point in time, the exchange rate will have changed. If you want to reconstruct the original output, you will need to obtain the historical exchange rate at the original time of purchase. No matter whether you query a service or subscribe to a stream of exchange rate updates, you will need to handle this time dependence. See time dependence of joins on page 475. Subscribing to a stream of changes, rather than querying the current state when needed, brings us closer to a spreadsheet-like model of computation. When some piece of data changes, any derived data that depends on it can swiftly be updated. There are still many open questions, for example around issues like time-dependent joins, but I believe that building applications around Dataflow ideas is a very promising direction to go in.